Volumes with known cross-sections, another example. So this is a very straightforward example. Suppose our base is just a right triangle as shown, going from 0, 0 to 6, 0 to 6, 3. And what we'd like is to have cross-sections that are squares. And of course, these squares would be perpendicular to the page. This would be the base of the square, and then rising up from that base. And we get a volume. So first thing we need to know is the equation of that line there. Well, that line's very easy to find. It's just a line for the origin, slope of 1/2, so it is 1/2 x. And that y is the side of the square. And so the area of the square would just be y squared. And putting this in terms of x, that would be 1/2 x quantity squared, or 1/4 x squared. Well, that's a of x, which is very easy to find. Well, now the volume is just the integral of that a of x, the integral from a to b of a of x dx. So this is going to be the integral from 0 to 6, the integral from 0 to 6 of 1/4 x squared dx. Well, the 1/4 comes outside. The antiderivative of x squared, of course, is x cubed over 3. And we're evaluating this at 6 and at 0. Well, at 6, we plug in, and what we get is 6 cubed, which is 216 over 12, minus 0, and 216 divided by 12 is 18, and 18 is the volume. Well, in this particular case, we're able to use basic geometry formulas to corroborate our answer. So if we go back and look at this, we realize we're building squares, so what we get, I'll just draw roughly, what we have here is on its side a square-based pyramid. And the base of this, of course, this is a length of 3, this is a length of 3, so the base is a square of size 9. The height is this length right here, so that height is 6. And so the volume, of course, volume of a pyramid, 1/3 base times height, 1/3 9 times 6, and that also equals 18. So it turns out that for this particular shape, which we can find with geometry, the work with calculus matches what we would expect from geometry.